Hello everyone, my name is Roy Jafari and I would like to welcome you to another video of data mining series. In this video, we are going to focus on yet another unsupervised dimension reduction method. This method is actually not just for dimension reduction. It's a very useful and general method that we know as functional data analysis. In this video, we're going to see what it is and how we possibly can use it as the purpose of unsupervised dimension reduction. Okay, let's look at these slides. Alright, so this is what we're going to have in this video. After a few recaps that we're going to talk about the distinction between supervised and unsupervised dimension reduction. And of course, we're going to talk a little bit about the previous unsupervised dimension reduction that we saw, which was principal component analysis. We're going to dive into functional data analysis, and like always, we're going to look at examples. So we drive the learning home the best possible way. So as we discussed, the difference between supervised and unsupervised dimension reduction is that the supervised dimension reduction focuses on the classification and prediction task, and it is done to help the these tasks performance. Basically, wherever we have the connection between independent attributes and dependent attributes, and we want to predict or classify the dependent attribute the best possible way, we do supervised dimension reduction for that purpose. But as we saw, principal component analysis in the previous video has a more general purpose as it is an unsupervised dimension reduction. And when we do this types of dimension reduction, we don't have a task in the end. We want to make it more successful. Our goal is to reduce the size of the data in such a way that we reduce the size. Basically, we remove the fluff. At the same time, we keep the most important part of the data. We did see that principal component analysis, which we call it a non-parametric dimension reduction, basically transform the axes of our data in such a way that our correlated dimensions becomes orthogonal or not correlated. At the same time, the most amount of variations were pushed to the first few PCs or the first few new dimensions. So here we want to learn a new unsupervised dimension reduction. Like I said, functional data analysis, this new method, is not just a dimension reduction method. I mean, if you can look at the name, is functional data analysis. On its own, it's an analytics tool, so it can be used for different purposes. But here we are going to see how it can be used as dimension reduction. Basically, what functional data analysis is re-representing the data for different purposes. So we are not talking about the purpose. Here the purpose is dimension reduction, but re-represent the data by the parameters of a function that can simulate how the data look like or what the data shows, and sort of capture the patterns and the trends in the data. So that function can simulate the patterns of the data. So like I said, you can have different applications, and it is, when we use it as a data reduction or dimension reduction method, it's an unsupervised dimension reduction that is parametric, unlike the principal component analysis. We will see what we mean by that in this video. So let's look at the example. This is the same example that we saw for PCA. We basically wanted to sort of see the trends between the countries as far as their happiness indices from 2010 to 2019. Remember that we had 90 attributes. So we had 9 happiness indices, and we had 10 years. So we had 90 attributes, and we also had 122 countries. Remember, at the end of the PCA, what we managed to find the 3 PCs, and we managed to explain 75% of the variation in the data. And since with only 3 PCs, and since this was only 3 dimension, we're able to visualize and sort of come to a visualization that summarizes all of our data, which is a significant achievement. So that's what we did for PCA. But here, our goal is going to be sort of like, look at it from a functional data analysis perspective. So if we were to, look at each of the happiness indices across the years for each country. So what we are looking at, the chart above here, we're looking at these numbers. We're looking at these numbers. And when these numbers are, plotted in the, sort of a line plot, from 2010 to 2019, and of course, if you pay attention to these numbers, there is unfortunately not a complete overlap because this is like 4 point something, but this is, negative 0.6, and the reason for that is because these attributes are standardized. But anyway, imagine that we put these numbers in a chart, and then we decide to sort of like fit a linear function here, right? We say, there is a linear function that sort of capture all of these 10 data points. And, when we find this linear function, now instead of having to have 10 numbers for these 10 data points, we can only have 2. So we can only show this by the parameters of a and b of the linear function. So that's what functional analysis is. So here we use a linear function to account for these 10 points for each of these happiness indices for each country. So instead of having 90 columns, which were 99 happiness indices and 10 years, we're going to have 9 happiness indices, of course, and for each of those happiness indices we're going to have 2 parameters of the linear function, which is a and b. So it's going to be 18. So we reduce the number of data objects from 90 to 18. So that's basically what happens, right? When we apply FDA in this way using linear function, what we do, we reduce the size of the data from 90 attribute to 18. So these were 90 attributes, if you remember, and this is, we only have 18 here because we have 9 of these, right? You only are seeing 4 of them, but there are 9 of them. Like the same here. I mean, some of them are not just shown here. Some are not shown here, the same here. So we have 9 of these. Alright. So that's what we did. We managed to reduce the size of the data significantly, at the same time keep the most important parts of the data for ourselves. So if you pay attention, the difference between PCA and FDA here is that with PCA we managed to reduce the size of the data from 90 to 3, right? So we were reduced from 90 to 3, and here we reduced the size of the data from 90 attributes to 18 attributes. While it seems that PCA has done a more significant job, if you pay attention to functional data analysis, you can see that even though PCA managed to do the data reduction, bring it from 90 to 3, more significant cut, but it came at the cost of losing around 30% of the informational variation in data. And that 30% that we lost is not just any 30%. It's a 30% that we don't know what it is. We're sort of blind to that 30%. But with FDA, we exactly know what it is that we are removing here. I mean, it's important for us when we do functional data analysis in this way. We say the trend of the countries is important for us, where they were and how are they changing. At the same time, where they were in the beginning. So we are reducing or throwing away some of the data. So this variation is data, right? This variation is information, but we're throwing that. We say, okay, we just want to keep with this line. but we are doing it in a much more controlled way. We're not blind to that reduction, and that's a really good distinction between functional data analysis and PCA as far as dimension reduction. So let's talk a little bit about what are the challenges of doing functional data analysis. I mean, of course, the most important part of the challenge is that finding that function that can actually simulate our data, right? So let's talk a little bit about how they can be done. First of all, there are a few famous functions. The list of them are here that you can sort of go to see if the data that you have can be simulated by one of these functions. The good thing about these functions is that they are famous, and there are a lot of resources out there for you to be able to learn. I mean, the few things that you want to know about these functions is that how they behave, and what is the meaning of the parameters. What those parameters mean for these functions. For example, it's important for us to understand that here, for example, what is the meaning of a and b for this linear function we just did, right? For our a for this set of points is 4.3. It's the intercept. It's where the data starts, where the country is for that happiness index. And then b is the most famous parameter of linear function, is the slope, is the rate at which there is change, right? So those are the two things that we keep from each happiness index for each country, where it was and the slope of change. And because we do know what these are, what do they mean, that can be used as an analytic tool on its own and a standalone functional data analysis. But not only that, we can also compare these parameters and they still make sense. So for example, here on the left, we see the healthy life expectancy as China at birth. It was at 67.1 in 2010, and it had a improvement slope of 0.22. And now we can compare that, for example, with the United States healthy life expectancy, which was above China before, 68.8, but it has had a very slow decrease. If you look at the sign, this was an increase, this was an increase, but this is a decrease. But the slope of change, which is decrease, is not as fast as it was for the China's increase. So we can compare these values and they still make sense, and they have analytics tools. At the same time, we can use these parameters for any algorithms, clustering, classification, whatever you name it. These are what is important for us from those data. I mean, where each country was and the slope of change. So looking at these parameters like A and B, now for each country we have an A and a B for each of these happiness indices, right? We know where the country was and the slope of change, right? So these are parameters that they have meaning we can use for analysis. Let's say if we do clustering analysis and we see these, we can use those as a way to understand different clusters. But if we were to use PCA, what we would be seeing is just some capsules of variation, some containers of variance, and they don't have any meaning, and that's why they are non-parametric. So that's why ever since we started learning about PCA, I kept talking about PCA as a non-parametric method, and FDA is parametric method. Of course, the lead time to do a PCA is just 0. You just decide and you do a PCA. But to be able to have functional data analysis, there is a longer lead time. You have to find that function, get to know the function and all of those things. By the time, if and ever you find that function, you might be able to do the functional data analysis. But if you do that, then you have a controlled version of functional dimension reduction that is superior than PCA, which is sort of like you're blind to what's happening. But at the same time, it's something you can just apply to any data. That's the advantage of PCA. All right, so one more thing we need to discuss about functional data analysis is that the famous functions that we saw, they're not just one function. They can you can increase and decrease their complexity. I mean, each function has, like I said, the behavior, but you can also increase or decrease the complexity. For example, the sinusoidal function, you can have one term, you can have two terms, three terms, and so on and so forth. And when you move from one term to two term, three term, your number of parameters increases. And of course, the complexity of them increases. To understand this better, let's look at this example. So we have here the 9 data objects. Each data object is presented with 100 attributes. Each of these attributes is a vibrational signal, and these 100 attributes together show 100 milliseconds, which is around 0.1 seconds of data. And when we look at these attributes, these data objects, all of them are ups and downs, oscillations in the engine's working, right? So these are what the sensor picked up from each of these 9 data objects, which are from different engines, right? So now, the sinusoidal function might be able to help us to sort of capture this oscillation. So, for example, we can apply the one-term sinusoidal function, and we see that it does capture around 85%, which is the R square here. But we do see that it sort of like it's not able to capture exactly where these these are the differences. This one is exactly the same as this one, but this is like a little bit like larger. This one is a little bit like smaller. That's why maybe we need a more complex function. So we tried this sinusoidal with second term, and we do see that now we managed to sort of like capture this length of them. They are like these are captured. I mean, this is perhaps larger than this one, and so on and so forth. But we still cannot capture the height of these. I mean, this is taller than this one, but it hasn't been able to capture that. So maybe we need to move to a more complex one. And when we move to that complex one, we do see that this complex sinusoidal function can, with 3 terms, can actually capture the ups and downs and oscillations in this engine pretty nicely, right? So it reached to 98% explanation, or the R square. So we say, okay, that might be a good fit. So we apply that to all of our other data objects, and we realize that this is actually indeed a good function to simulate our data. So now, if you will look at what we managed here, we managed to move from 100 attributes to only 9 attributes, right? Not only that, these 9 attributes are parametric. I mean, they have meanings to them. And also, if you pay attention here, we also sort of managed to smooth the data, right? I mean, this is a perfect way to capture all of the patterns in the data at the same time. The errors are sort of like gone, right? So, for example, these are sort of like random errors there, so the errors are also gone. So, one thing we need to pay attention here that, and like I said, FDA is not just a functional. It's not just a unsupervised dimension reduction. It could be used as data transformation, data massaging, data reduction, and data analysis. Here we did kind of use it as data reduction because we reduce the data. At the same time, we transform the data by making sure that there are no noises. At the same time, we brought the most important things in our data, which are these oscillations and their length and their heights, right? So all of these, we managed to bring them to the surface, right? We were able to do some transformation in the data that what is more important for us is pushed to the surface. So now any algorithms can actually use these for any types of analysis, and that is called data massaging. So, like I said, FDA is a very useful branch of analysis, and it is truly its own world. And you could spend so many hours of learning about FDA. I mean, each of those functions that we looked at, it can be learned. It has many sort of like properties, parameters have their own meaning. So this is basically a simple introduction to that world, and as a sort of like a way of unsupervised dimension reduction. Also, it is a very useful method for doing that, because it sort of like captures all of these steps at the same time. So whenever you are doing some functional data analysis as an unsupervised dimension reduction, probably you're doing all of these at the same time. All right, so let me offer you some summary of this video. In this video, we talked about some recaps in the beginning. We talked about principal component analysis and the difference between supervised and unsupervised dimension reduction. And then, of course, we compared PCA and FDA at different points during the video. And of course, we have had two examples. One, we use linear function to reduce the size of our data set that we had used for PCA as well. And then we had another example that we saw we could use more complex sinusoidal functions to actually capture what we need by just making the function more complex. We're able to do a better job at reducing the size, at the same time bringing the what is important from the data for us to the surface. Until the next video.